So, I think not too much time, so let me turn everything over to Jim Weaver.
Thank you, Frank. Yeah. So, my name is Jim Weaver. Here's my coordinates. Reach out to me anytime. I work for Pivotal, and I actually work out of my home office in Indiana. Written several books on Java, and I work for Pivotal, and we steward Spring, Pivotal Cloud Foundry, which is a cloud platform that runs on all the major cloud platforms as well as on-prem, so developers just have to push to one platform rather than having to understand all the internals of the other ones, the APIs of the other ones. Also, we have a labs, Pivotal Labs, where we engage with customers, help them get up to speed on Agile processes and CI, CD kinds of things, continuous integration and deployments, and just help them get going with projects. And then the new kid on the block, as far as Pivotal is concerned, is PKS, which oddly enough stands for Pivotal Container Services, which is production-grade Kubernetes. So we have all sorts of nice technologies, but my favorite thing about working for Pivotal is our principles and practices. 3 of the 5 are do the right thing, do what works, and be kind. And I mean, so I feel like I'm a pretty kind person. I don't need a company to tell me to be kind, for me to be kind, but it's refreshing to work for a company where one of their core principles and practices is to be kind, especially in this day and age. For God's sake, let's be kind to each other and treat each other the way that we would want to be treated, right? And so it's refreshing to work for a company whose core practice is that. I'd like to invite you to San Francisco in December. There's a Spring One platform gathering, and it should be a really good time and learn a lot about Spring and some related technologies. And so I talk about machine learning, and so people sometimes ask me, what's Pivotal's involvement in machine learning? And we have actually quite a bit. One is that we steward a project called Apache Madlib, which is a data machine, or big data machine learning in SQL, open source thing that's in Apache right now. We also have lots of Spring families. One is Spring Cloud Data Flow, which is the ability then to stream data and configure the streams of data, and also, while you're at it then, maybe hit up some prediction or analysis capabilities and perhaps TensorFlow or some other machine learning libraries. So lots of involvement and interest in machine learning. Before I get too started, actually too far, and everything I'm going to say right now is not true. It's just to be funny, but. So my boss has trust issues with me, and he sends me all over the world to speak about stuff, but he doesn't really believe I do that unless I take a selfie with the audience. So you can help me out by posing for a selfie. He also requests that you do a crazy pose, because I want to show him that you're enjoying the session and having a good time. So I'm going to ask you at the count of 3 to do a crazy pose for me. Is that cool? You okay with that?
Yeah.
All right. Ready? 1, 2, ready? Crazy pose. Nice, nice, nice. So I'm actually going to tweet this. So if you've told somebody that you're going to be somewhere else other than here, you could start thinking of your of a story. Okay. So we've tweeted it. Speaking of tweet, the slides that I'm going to use are actually online. They're live on the web slides. And let's see. So if you go to my account, just twitter.com/JavaFexpert, then my, oh wait, look at you guys. Look at you all. Oh, what a handsome group. Oh, I'm very crazy post. Thank you. Thank you. Nice. Anyway, the one before that is the slides that I'll be presenting. So you can follow along if you wanted to. There are lots of links to demos and resources in here, so I encourage you to click that link, get the slides, And you can follow along now if you'd like to. So when I got into machine learning, there are two things that I did to try to get up to speed. One was I took this Coursera course by this fellow by the name of Andrew Yang. Anybody heard of Andrew Yang? Okay, good. So some of you have taken this course? Okay. Yeah, it's a pretty rough course, but it's a really good one. And so what I'd like to do, with his permission actually, is play you a snippet of the introductory video to that course, where he kind of talks about what machine learning is, and I think he's got a good perspective on it. So here's Andrew.
What is machine learning? You probably use it dozens of times a day without even knowing it. Each time you do a web search on Google or Bing, that works so well because their machine learning software has figured out how to rank web pages. When Facebook or Apple's photo application recognizes your friends and your pictures, that's also machine learning. Each time you read your email and a spam filter saves you from having to wade through tons of spam, again, that's because your computer has learned to distinguish spam from non-spam email. So that's machine learning. It's a science of getting computers to learn without being explicitly programmed. One of the research projects that I'm working on is getting robots to tidy up the house. How do you go about doing that? Well, what you can do is have the robot watch you demonstrate the task and learn from that. The robot can then watch what objects you pick up and where to put them and try to do the same thing even when you aren't there. For me, one of the reasons I'm excited about this is the AI, or artificial intelligence problem. Building truly intelligent machines which can do just about anything that you or I can do. Many scientists think the best way to make progress on this is through learning algorithms called neural networks, which mimic how the human brain works. And I'll teach you about that too. In this class, you learn about machine learning and get to implement them yourself. I hope you sign up on our website and join us.
So one of the key things that he said that I think is a really good definition of what machine learning is he said it's the science of getting computers to learn without being explicitly programmed. So everybody in this room knows how to make a computer do something. You know, you can teach a computer to do something by writing code. But with machine learning, you use data and algorithms and models, and you feed models with the data so that it can learn. And so you're teaching it to learn without explicitly programming it. So we see it everywhere, right? Self-driving cars are starting to come online. We've got image descriptions, like you could take an image and machine learning can then pick out the subjects in the image, as well as take a stab anyway at figuring out what they're doing, what's going on, and then creating a description in some language of what's going on. So there's several levels of machine learning going on. So if you're a top-down thinker, if you like to put things into categories, then you'll appreciate that machine learning has just three and only three categories. One is called supervised learning, one is called unsupervised learning, and one is called reinforcement learning. So I'd like to go into this really quickly, and then we'll dive into each one later. So supervised learning is where you give it data, you give the model data that has the right answers in it. So in this particular case, it's a very simple model. It's got one feature, one input, and that is size in square feet. It's got one output, which is price in dollars. And then we have data points here that are just data of houses where the size in square feet and the price in thousand intersect. And then these blue lines are attempts, two different types of fitting that data. So this would be a line trying to fit that data, perhaps not so well. And then this is a quadratic curve that tries to fit that data a little better. But the objective then is to be able to take a house that you haven't seen before, perhaps 750,000 square feet or 750 square feet, and then figure out, based upon how you fit the model, let's see if we fit it with this line, then we're going to predict that it's $150,000. If we believe this quadratic curve fits best, then we predict that it's $200,000. So So that's a supervised learning in a nutshell. It's a very simple model, but this particular one is very simple. One feature, one output, but it's where the data, you're feeding it the right answers. In this case, the right answers are the prices. Now, this particular machine learning problem is called a regression problem because the output, that price in thousands, is continuous. So it's called a regression problem. You could also have categorization or classification problems. And that's where you would, the output would be some category, like this is a bird, this is a dog, this is a cat, that type of thing. So, and as we go along, if you have questions, please do ask them. That'll help me tailor this to this audience and to answer your questions. I know we've got till 8:30, and so I'll take the responsibility of managing the time, so if I feel like a question's going on too long, or whatever, I may defer it, or say let's cover that a little later, maybe after the presentation, but please do ask, and then I'll manage the time. Okay, so unsupervised learning, you give it data, you give the model and the algorithm's data, but you don't give it the right answers. The data is just unstructured data. And then one example of it, unsupervised learning, might be clustering. That's one of the earlier algorithms, K-means cluster, where you might give it data that has a market segment information or social network information, and it tries to find, then you're asking it to find the centroids and the clusters. How does the data fit? So it's unlabeled data. You're not giving it the right answers, but you're saying make sense of this and help me interpret it and help me visualize it sometimes. Then the third type is called reinforcement learning, and that is characterized by having an agent. Could be a robot, could be a gameplay agent, could be some other kind of agent, and you're giving it a reward for doing something correctly, for doing a task correctly. And so that's why it's called reinforcement learning, because you're reinforcing it. And its job then is to maximize its rewards. So one recent success story was AlphaGo, where using a combination of reinforcement learning, unsupervised learning, and supervised learning, it beat the world champion Go player. This was a project by Google, DeepMind, something like that. So I'd like to dive into supervised learning now. So we'll go into that. So one of the Hello World data sets of the data science world is called the Iris Flower data set. And it's the Hello World because it's very short. It's only got 150 rows. And it's only got 4 features, 4 inputs, and those are the petal length and width and sepal length and width. In addition, it has one label with 3 classes. Iris, the species, right? They're Iris setosa, versicolor, and virginica. And so this data set is a good one to introduce people to machine learning or data science, because it's one that's very it's small, it's finite, it's very easy then to go from the feature, to train it to go from the features to the labels. So if you think about that problem a little bit, if we have 4 features, in order to be able to train a model, we're going to have to be able to distinguish, kind of compare those features with each other in different perspectives, in order to find decision boundaries between them, so that then we can find those decision boundaries to successfully classify the outputs. So here, we've got 4 features. Those are 4 dimensions. Well, humans are, we're used to thinking in 2 dimensions or 3 dimensions. When you start thinking about 4 dimensions or 100 or 1,000, it's a little tougher, and so you have to start either thinking in terms of just trusting the math, or using some tools to visualize more than 3 dimensions, to do what's called dimensionality reduction down to, let's say, 3 dimensions.
Excuse me, sir.
Yes.
Is there any way to make the text a little larger?
Oh, sorry. the text a little bigger?
Yeah.
Okay, I'll try to be sensitive to that, and we'll zoom in. As a matter of fact, I'll zoom into this one. Or the, like this text right here is pretty small, isn't it? Yeah. Okay. I will try to be sensitive to that and zoom in when I can. So this is just there's a data visualization tool. It's part of the TensorFlow project. You can get at it by going to projector.tensorflow.org. And if you click this link, then you get to this. And this is showing the iris flower data set, showing the 4 features, mapping out these 4 features. You know, we see the classifications here: iris, setosa, and versicolor, and virginica. But remember, they're made up of 4 features, and we're seeing that in 3 dimensions. So this, yes.
Forgive me, I'm a tiny bit confused. When you say there's 4 dimensions being displayed, it's 2 operands, the pedal and the sepal, with 2 dimensions each, right?
Yeah, I mean, there's just 4 dimensions. 4 dimensions altogether. Those
Okay,
4.
4 dimensions on 2 different, it's 2 dimensions per, the pedal and the sepal are 2 things with 2 dimensions each, right?
Okay, so the question is,
Yeah.
you know, where do we get the 4 dimensions?
Yeah,
So, the machine learning algorithm doesn't know anything about irises or anything like
Okay.
that, petals or whatever. So, as far as it's concerned, there are 4 separate features, and
okay,
yeah, we think about them as, you think about them as.
okay, yeah.
So then, I just had a conversation with a colleague just a little bit ago as everybody was walking in, and he was telling me that 40 years ago, he was, or not 40 years ago, but several years ago, he was very interested in AI, went to college and stuff, and part of his research was in AI. But that was before the end of the AI winter. So the AI winter is this period of time when people started talking about using the brain as a model for algorithms and programs that would learn, right? Back in the 70s and maybe even before, people were thinking, since the brain can learn, why not have machines, why not model machines after the brain, and so the machines can learn? Well, that was a great idea, but Moore's Law hadn't caught up with it back then. And Moore's Law that says that you can double the amount of transistors in a square centimeter every 18 months. You turn that crank every 18 months, and finally, maybe 5 or 6 years ago, Moore's Law caught up to where it can, we can realize that vision of being able to model the human brain in software. Because it takes a lot of processing power to do that. It takes a lot of storage, a lot of memory, a lot of data storage, and so we've got the parallel processing and all those kinds of things. And so finally, that's why we see, with some great research, of course, that's why we see in the last 5 years or so that machine learning has really come on board and become very, very useful and very powerful in everyday things. And oh, by the way, people like Andrew Ang and other academic researchers are being paid like rock stars and sports figures because it's a very in-demand kind of thing. So the brain over on the left has neurons, the fire, the whole information in fire. It has synapses that connect the neurons. It's got dendrites, which are input. It's got axons, which are output. And those are all modeled then in software with artificial neural networks, sometimes called deep networks. By the way, the reason they're called deep is because they have more than one hidden layer. They're deep, right? But so the input layer is over on the left, and it has features. So there's one input, one neuron for each feature. Well, if it was the iris data set, how many features would we have over here on the left? 4, okay, good. And then the output is, if it's a classification problem, you're going to have one output for each, output neuron for each class. So how many is up with the iris data set? 3, okay. And so then between those, then we have hidden layers, which each hidden layer has a number of neurons, and each neuron then is connected with every other neuron in the adjacent layers. Okay? So it's called a fully connected network. Artificial neural network, deep belief network, they're all kind of the same. They're all talking about this. So the other thing I did besides take this, yes?
So is the layering one of the important concepts, or is it that the lower layers could connect back to the previous layers as well?
Okay, so the question is, I believe, is the number of layers?
No, so is it like the layering is important, or the blue can connect back into the feed into the green as well?
Well, it's not that the layers, the more layers that you add, the more complex learning you can have, right? But when you're talking about connecting back, right, there are ways that you need to propagate results back to the beginning in order for you to correct. And then that's part of the learning process, right? You come up with a result and then you back propagate those results. And they say, okay, I need to adjust this in order to come and calculate more.
I'll for sure get into that. I want to make sure that I understand your question completely. So, so we have a number of layers, right? And so I think you're asking, are the layers important, or is it more the connection between the layers? And it's really both. They're both very important. And as my colleague here is talking about, we'll then get into some of the techniques as to why they're important. Is that help? Okay. So one of the things that I did besides take Andrew Ng's course, yes, sir.
If you could go back to the layer slide.
Yes.
So, I mean, can I consider them as in a graph or different nodes? And what exactly are these? The different nodes in a graph kind of thing? What is the balance? Is it kind of a data structure, or what is this exactly?
Okay, so the question is, could you consider those as like nodes in a graph, or what does this really mean? And when we get into implementation, you know, how do we implement this, right? And so I'm going to get into that, but you can think of it as a graph where you have nodes and edges, and each node is fully connected with the other nodes and the other layers. Later, we're going to assign weights, like values, for each of those nodes and edges. And so, yeah, Frank, I'm really impressed with the way your group asks questions. That's awesome.
And if there is a new discovery in this process, if we have fourth output, that means we will train the, I guess, these layers and network again to, I guess, to identify that fourth output.
Okay, when we get past, when we get almost to the end of supervised learning, will you tickle me again on that? Because I want to fully understand that. Thank you. Yes.
Just for clarification, you mentioned that the graph is fully connected between layers. Is that always true for a whole neural network?
Okay, so the question is, the layers, is it always true that they're always fully connected? And the answer is no, it's not true. And I'll show you some cases where that's not true. You guys are awesome. You all are awesome. Yes.
Yeah, there was one other thing that I was kind of mentioning that what differentiates this from a typical graph is the fact that when data is flowing from left to right, it's not like you're going from one node in the next layer and then going back, right? When somebody said it's a weighted graph.
Right. Good point. So what my colleague is saying, tell me your name.
Raphael. Sorry.
Raphael. What my colleague is saying is, you can picture this as a graph, but as you'll see in a minute, the direction is one way. So it's a feed-forward mechanism that makes these predictions. And so I'll definitely cover that. Thank you.
It's not a cyclic.
It's not acyclic. No, it's not like a DAC, directed acyclical graph. So when I first started learning machine learning, one thing I did was I took Andrew Ng's course. But being a Java developer, Java and Spring developer, the other thing I did was I wanted to create a visualization that helped me understand exactly what's going on underneath, inside the neural network. And so I titled this talk, by the way, Machine Learning Exposed, because I wanted to peel back the curtains so that I and you could see kind of what's going on underneath, as we obviously want to see by the questions, which are awesome. So this application that I created is Java and Spring on the back end, and then front end using a visualization library as well as Angular 2. I may port that to JavaFX at some point. So anyway, we've got a visualization here then for iris flower. So I'm going to click that again here, and I want you to see the numbers update. See, as I click this, the numbers update. And what's happening is that they are learning. Each of these synapses and neurons are being updated with weights and biases that will help us with this feed-forward calculation, which I'll talk about in a second. So let's say that I see this, I observe an iris flower in the wild, and I want to know what kind of iris flower it is, what species it is. So I can measure the sepal, and maybe the length is 5 centimeters. The sepal width, maybe it's 2. The petal length, maybe it's 2. Petal width, maybe it's 2 centimeters. And then I make a prediction, and the model then tells me that there is a 0.52 probability that it's Iris virginica and a 0.48 probability that it's Iris versicolor. And so the jury's kind of out, right? It's a little bit better chance that it's an Iris virginica, but that's the prediction based upon how it's been trained. So how did it come up with that prediction? So that's what the next slide's about. And that's this forward propagation, this feed-forward mechanism. Now to go into that, I'm going to show you an even simpler neural network that has just one hidden layer, 2 inputs, 2 outputs, and 2 nodes in the hidden layer. And this neural network, just as a toy example, models the XOR logic gate. So, being a room full of Java developers, I'll ask you this question. Let me get to the XOR. So if I said true on an XOR gate, if I said true XOR true, what would you expect the output to be?
False.
False. Exclusive OR, right? So the model says, yeah, there's a 1 probability that it's false. So the question then is, how did it go from the input through the network to correctly predicting the output? So that's what we'll talk about now. That's called forward propagation. So with the network, we have the inputs, we have the weights, we have the biases. There's some more weights. We also have something called an activation function. That's part of the neurons. And activation functions are the characteristics. They define the characteristic of how a neuron fires. For example, here's a picture of the function that we'll be using in, these are sigmoid neurons, sigmoid activation functions. That's the curve for the firing characteristic of a sigmoid activation function. So as the input increases, then it fires kind of in this pattern. It gets higher in this curve. And that's important, as you'll find out, in how a neural network can retain information, how it can learn. by these firing patterns, yes.
Yeah, Jim, I'm sorry to interrupt you again.
No,
You have two operands that are going to take the inputs to an XOR learning ambition.
yes.
Okay, now in that, what is the significance in the weights to get that? It's trying to learn what an XOR computation is based on. Could you describe what the weights are again in that ambition? Did I say it right? You have two operands.
No, you said it perfectly.
Okay.
And it's a perfect lead into my next slide.
Okay, I'll let you
I
go.
appreciate
Sorry,
that.
sorry.
No, no,
Yeah.
no. I appreciate the help. And so,
Quick question,
yes,
you said that those fire, right, we're sort of, I guess implicitly, you're assuming that it's binary, that it's a 1 or a 0?
that's a very good question. As far as like a neuron firing in an artificial neural network, it's not a binary thing. We think of it as a binary thing, but what it really is the and when I get into the calculations, you'll see. But it's like this curve here. The output will increase at this rate as the input increases, and that output, the value of the output, is what's used in subsequent layers. And so you'll see that.
And is that bound then between 0 and 1, for example, or?
Is it bound between 0 and 1? It's typically between 0 and 1, yes. Yes. Okay, so here's the calculation we use to get between inputs and outputs. And so it's middle school math, and this last step is high school math. So you all be comfortable with this. So the calculation assumes that you've got a neural network that has numbers in it, weights and biases. So I'm going to talk about where those numbers come from in the next slide. So just assume that we've gone through some training process that trains those numbers. So once we've got those numbers, then when you input something, then you go through the following calculations for every node in every layer. And here it is. So let's, for example, take this node. So we multiply the inputs by the weights. So here's the node. We're going to multiply this 1 by this weight, and then add that to this 0 times this weight. So that's this calculation up here. 1 times 8.54 plus 0 times 8.55, that equals 8.54. With me so far? Yes, okay, good. So then we add the bias. So we take that 8.54 and we add this bias, which is minus 3.99, and we get 4.55.
And what does bias represent in terms of the ambition to learn an XOR computation?
So what is bias? So what bias is in very simple terms, it ends up, because of this calculation, it ends up being as part of kind of added to the input to then cause it to fire faster or slower. So it has to do with something with firing rate.
Okay.
Yeah. So anyway, so we take that, after adding the bias, we take this, the 4.55, we negate it. This is where the high school math comes in. We negate it, and we use that as an exponent to the constant e, 2 point whatever it is, and then add 1 to it, and then we use the inverse of that. And that is, this over here is called the sigmoid activation function. It's just a standard function that defines this curve. And so in this case, it ends up with 0.99. So now the value of that neuron is 0.99. And so then we do that with every other node in every other layer, and then that propagates all the way to the answers.
Sorry.
Yes. Okay. So now, any questions on that? Forward propagation. How do we get from the input to the output? Okay. Yes.
where does the 12.53 factor in? It's, you showed all the calculations, but then the one from sigmoid to the output, you have those numbers. How does that factor in the calculation?
Okay, so which number?
The 12.53.
12.53. Okay, the 12.53 then is a weight for this synapse or this synapse. So these are all weights. And then thank you for that question, because that leads me to the next one. That these weights were already there after we trained the neural network. So now I'm going to go to how do we train a neural network. Okay. So that answers that question, right? Okay. Okay, so how do we train a neural network? Well, that's something, as my colleague over here talked about, as being back propagation. So the forward pass does the prediction, so it assumes that you've trained a network. The back propagation trains the network. That's part of training a network. So how that goes is, first of all, you seed all the weights and biases with a very low random numbers, or a set of very low random numbers. And then you take all the data and you apply that forward propagation to all the data. And when you do that, because you've seeded the network with very low random numbers, the results of the feed-forward propagation are always going to be different than what the true right answers are in the data, because you haven't trained the network and they're just random numbers. So it'll always be wrong, but it'll be wrong by some amount. Right? It'll be wrong. It'll be maybe when you forward propagate it, it's going to be maybe very low answers because you use low random numbers, and the data is correct, but there'll be a difference between those, and that's called the cost, or the error, or the cost function, or the objective function. And the idea then, to be able to train the neural network, is to be able to get all the cost you can out of the network, make it so that the feed-forward predictions, the feed-forward calculations at the end, are as close as possible as what the data says that the right answers are. So we get the error out of the network. With me so far? Okay. Yeah. Okay. So, how does the back propagation go? Well, to explain that, what I'd like to do is break it down into the first very simple example, and that is the house pricing. So we're going to, with the weights and biases, you have 1 degree of freedom for every weight and every bias, right? Because you can tweak the values of every weight and every bias. And so each one of those in the math or ML world is called, machine learning world, they call those thetas. Everything's a theta for some reason. And so we're going to take it down to 1 theta. And that theta is going to be the slope of that line. So we're going to use the house pricing example. And I'll zoom in on this a little bit. We're going to use the house pricing example with the square feet on the x-axis, the prices on the y-axis, and then we've got data points here that represent the house, our data, and then we've got a line here that represents a first shot at trying to fit that data. Now the error in this data, the error in the model then, can be calculated very, very easily by taking the distance between the y distance, the vertical distance between each of the data points and the line. So there's this much error between here and here. For statistical reasons, they tend to take the squared error and then average them. So what we have over here then in this table is the mean squared error as the difference between the line and all the data points. So that's the mean squared error of those. So taking the squared error of each one, adding them up, and then taking the average, dividing it by 10 or whatever it is. So that's the squared error. So now we want to reduce that error to train the model. And I said we're going to use, yes, question?
How is the first shot somewhat accurate?
Okay, so how is the first what?
Well, it's sloping upward, which is right. How did it get its first shot somewhat right?
Okay, so the question is, how did it get that first shot somewhat right? Okay, so this was created by a colleague, Catherine Beaumont, who I'll mention a little bit later, that just used this slide that created this slide as a tool to teach this. So this wasn't actually the product of a production machine learning algorithm. It was just
Expect that.
right. So you wouldn't expect it to be that close. Correct. Yeah. I could have said it just in 5 words. Sorry for 25 words. Okay. So now we're going to change one theta, and the theta is the slope. And we're going to go ahead and increase the slope, which is the rise over the run. And then you would then measure the error again. And if we increase that slope a little bit, increase the rise, then we would expect the error to be less. Right? And so then the challenge is, well, how do you know how much to increase the slope? And by what increments do you do that as you're training and all that? And so in machine learning with backpropagation, one very prevalent technique is something called gradient descent. And gradient descent then is like it shows on this graph, this hand-drawn graph. At the bottom here on the x-axis we have one value, that's the theta, that's the slope. And so as we change this slope, maybe we increase the slope or decrease the slope, we could calculate the mean squared error in the graph. And that mean squared error is on the y-axis. So maybe if we play around and we increase the slope, and we find that improves, that reduces the error, then we're now here on the graph, and maybe we tweak it more, we add more to it, to theta, and then we see that it's here. And so as we're doing that, we're getting as low as we can go. And as a matter of fact, if we added more to the angle, to the slope, it would actually get worse. So that technique is called gradient descent, where we are descending a gradient, in this case, which is just one curve, trying to get to the bottom. Yes?
Sorry to interrupt you again. Could you go back one slide?
Sure.
Okay. Now, that line that says a y equals mx plus b plotted right there on there, now, does that represent an initial attempt? And when you say error term, is the correct term the least squares regression result of those points? In other words, what I'm trying to figure out is what does that line right there represent? Those points represent data. And that blue line there represents the first attempt. And then when you say error term, an error relative to the least squares regression function? Okay? In other words, error relative to what is correct if that has an error term?
So your question is, what's that line represent?
Yeah.
And that is a first step.
Okay, now the error on that line.
Now the error on that line is.
No, wait, let me interrupt you, I'm sorry. The error is relative to something that's considered correct, right? And is that correct thing a least squared regression?
Well, the correct thing would be.
A squared error.
If that.
Okay.
Yeah.
Okay, gotcha.
Reduced
Okay.
squared error.
All right, thank you.
Good. Okay, so my colleague Catherine Beaumont then created this really nice visualization, this application that allows you to visualize gradient descent. And so this is available in GitHub. It's licensed freely, and it's an application in JavaFX. And so here we have that same thing. We have data points, we have a line that tries to fit it, first stab. And then here's a button up here where we can start to play with that. We can start to increase that slope. So here we'll increase the slope to 1.05. And notice as we're increasing the slope, the line, we see the slope go up, but then over here on this graph, on the x-axis is the amount of slope, and on the y-axis, just like on our previous slide, on the y-axis is the cost, is the error. And notice as we're increasing the slope for this data, that the error is decreasing. But then, if I keep increasing the slope, the error increases. So there's this minima right here that represents the lowest error possible using that line. And so now I can, another part of this visualization is I can reset it, and I can pretend that I'm the learning algorithm, and I can take these steps down the gradient that we just talked about. So here I'll take a step down from here, and we can see, not being familiar with the curve or anything, but we can see as we're taking these steps, we can see a curve start to materialize, and then we can take a tangent line on that curve, and then take another little step and maybe decrease the size of the steps as we're going, and then end up converging as low as we can go. So that's the intuition behind creating descent. Yes?
Yeah. What's the motivation for you to increase the slope versus decrease the slope on the first attempt, for example? Which direction do you go?
Okay. So the question is, what's the motivation behind either increasing or decreasing? And so if you end up, let's say that you decide to decrease the slope, and then the error goes up, then you start increasing the slope because you know you've gone the wrong direction. So the first one is as far as I know, is a stab in the dark, and then you're trying to find. Once you have 2 points, then you can start to compute a tangent, right? I mean,
right.
Very simple.
So is that always a parabola for the gradient?
Okay, so the question is it always a parabola?
And then you compute the minimum for that.
So it's always some type of curve that looks like that. But when you get like you get into, let's say that we had more than one theta that we're dealing with. Let's say that we start, in addition to slope, we want to also allow the degree of freedom of changing the y-intercept. Okay, so now we have 2 thetas.
Right.
So here's this theta, maybe that's slope, maybe this is y-intercept along this axis, and along the vertical axis, then it's still the cost. And so as we tweak slope and y-intercept, we see this gradient, which now has 2 dimensions. You know, we can try to descend this gradient as straightforwardly as possible, and tweaking these thetas. Okay. Good. Yes, question.
Yeah, I'm having trouble seeing the connection between the graph for house prices and the answers that we were getting for the iris problem. The iris problem's answers were discrete. It's either this kind of iris or that kind or that kind. The graph, on the other hand, is a continuous, here's the price versus the... So how many outputs would there be in a neural network with just house prices? Would it be just one output, and we measure the intensity of the output of the final neuron?
Good, yes. So the question is, what would a neural network look like, right, that had a regression output rather than classification output?
And I guess ultimately my question is, let's say we get the wrong answer for the iris problem, how do we know which of those weights and biases to tweak? Or how would we get, would we just start goofing around and looking for a trough in that multi-dimensional
Okay.
Right, is that it?
Right, yes. So I'll take both questions here. The first one is, what would a network look like that was a regression output rather than a classification output? So one of the visualizations we have here is regression sum. It's kind of a fun little one, actually. It takes two numbers and adds them up. And so using a neural network to add two numbers, it's kind of interesting. So we've got an operand, one operand maybe 2.1, and one operand is 1.3, and we're making a prediction, and it says the prediction is 3.41. Right, so it was trained using data, lots of data, lots of addition facts, right? But the output, as you correctly assume, is one node, and the value of that node then is the answer. And then addressing your other question as far as like the error, so obviously you calculate error differently in a regression problem like the house problem than you would in a classification problem, because the error for that is, was it right or not, right? And so then, but there's still that error, and you could still have, there's still formulas then for the error, was it right or not? It's more discrete, and then you tweak the thetas to try to come up with, to try to make it, get the error out.
So then what I'm guessing now is, depending on the number of different, so each of these numbers in the inner part of the neural network is a theta. And so if there are, I don't know, 20 of them in this diagram, we have a 20-dimensional terrain to navigate and find a minimum, a local minimum. Is that what we're doing?
Okay. So let me restate, and that's so if in this diagram we had I don't know, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 nodes. That's 10 biases, and each of these nodes has 10 connections to this node, 10 connections to this node, 10 connections to this node. So there's at least 40 weights and biases there. So you then have this thing that you can't visualize, but it's a 40-dimensional terrain that then you have these troughs, these valleys in, and then the challenge in the gradient descent is then to find the minima. Sometimes it's a local minima because maybe you've gone down one that's not actually the deepest, but a lot of times that doesn't matter. But you've tried to find the minimum in that fabric. Well, these are great questions. This is like the best questions I've had in any machine learning audience I've ever presented to. No, seriously, this has been great. Kudos. So there's a really good book on, when you get into tweaking 100 weights and biases, how do you know, how much to tweak on each one? And so there's some pretty straightforward algorithms for doing that, for saying, oh, we'll tweak this weight this much, and this proportionally to this weight, and that's based upon local errors that are in a certain part of the network. And so there's a great book called Make Your Own Neural Network that really goes through blow by blow on how that's done, so I would recommend that. So the application architecture for what I showed you is, I just already said that, it's a single page HTML5 client, Angular 2 and Vue.js. And the backend uses Java and Spring and this deep learning for J library. The Spring helped me easily stand up REST services, and also as it was listening for the model and updating those weights on the client, I use WebSockets for that. So it makes really quick work of that. The Deep Learning for J library is here at deeplearningforj.org. It's a really great Java library for machine learning. And then here's just an example of the code in using Java and deep learning for J for configuring a neural network. It's a fluent API. Here we're seeding, remember, random numbers, low random numbers, so we're seeding the random number generator. We're telling it how many iterations over the data to train a neural network with. Here we're saying 300. We're giving a default activation function. Here it's hyperbolic tangent, which has a different characteristic than sigmoid does. Learning rate, remember when you're descending that gradient, well, how do you know, how does the algorithm know how big of steps to take? Well, you can influence that by giving it a learning rate. The bigger the learning rate, the bigger steps it will take. If you take too big steps, by the way, then what can happen is you can overshoot. And so you're jump, 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 overshoot, jump, jump, and you're kind of skipping over the bottom of the bowl. You're never finding the minimum.
And then too small a step, then it takes too long to train them.
If you take a smaller step, then you've got lots of iterations through the data. And if you're using a cloud API, let's say, then you're paying the cloud provider lots of money just to train your neural network inefficiently. Right? So a lot of times you'll train locally and then deploy in the cloud at prediction time. Right, to do the feed forward. Yes?
I noticed all the nodes in all these graphs tend to have the same activation function. Is that always true?
Okay, so the question is, the assertion is, you notice that most of the nodes in these tend to have the same activation function. And there are some reasons to use various activation functions, but you use them because of their characteristics. For example, if you have a classification problem, then I typically use a softmax activation function on the output layer, so that because softmax guarantees that the values of the neurons will add up to 1, which is what you want. You want the probabilities to add up to 1. And for various, like when you're experimenting with trying to get it to learn efficiently, you may find that for certain problems, the data modeled in certain ways, that it may be more efficient to use maybe a linear activation function, that looks just like a straight line, for ones where the data is well separated. And I can show, if we have some time, I can actually show you a neural network playground that I usually assign labs for when I do a workshop. And so that'll give you some intuition and something to play with to really get some experience with that. So then, so we can change learning rate, we can change regularization. So that has to do with introducing noise into the model, into the training. There is a danger of overfitting, where you can train the data, you can train the model too well on the training data, and to where it doesn't generalize when you get real world data, because it was trained so well on just that data you trained it with. And so one way you can fight that, there are a few ways you can fight it, but and you always, for example, when you train a model, you always save some of that data for testing, for test data, so you can validate whether it's been overfitted or not. But then also, you can use regularization to introduce noise so that it tends not to overfit. And then here we're defining the layers, overriding the activation function that we defaulted with softmax. So that's just it's an example of how you can define a neural network in Java using deep learning for J. Of course, it's a Spring project, so just go to start.spring.io. You can tell it what kinds of things you want in your project. You want REST services, WebSockets, you want database connections, you want streaming, things like that. And then you can generate a project. It'll give you a Maven POM and some starter code, and it's just like super simple. So here's that lab exercise. And if you go to this slide sometime, it's got some, it's a really fun lab exercise. So it tells you to take all of these 4 data sets. Like here are 4 data sets. One is a circle where you've got data points. You've got features that are inside the circle and ones that are outside the circle. And some other ones. Here's an exclusive OR. Here's one where it's just, it's called Gaussian, but it's very clustered to where it's very easy to find the lines between. And then here's a more challenging one that's a spiral. And so if we picked maybe the first one, the circle, and we just kept everything default here. We've got, you know, 1 input layer, we've got 2 hidden layers, we've got an output, and we start the training. And we'll notice this is how many epochs or iteration that's taken through the data, and then here is how the error is reducing. And so now we've got a pretty good error rate, you know, training loss, test loss, these are our error. So we've got the error out pretty well, pretty quickly. And then here is a visualization of how it has classified it. So it's found pretty well the things that are inside the circle and versus outside the circle. But if we tweak that, let's say that we used a different activation function. Maybe we use a linear one, and we hit play. We find that because of the characteristics of that function, which is a linear, is just a line, that it really doesn't learn very well on this particular problem. But then if we use that linear function over on this one, where we expect an activation function that looks like a line to be able to find that, to be able to distinguish those, then there we are. You know, it just found it right away. A rectified linear, the characteristic of a rectified linear looks like a hockey stick, vertical and then a 45-degree angle. So if I applied that, you know, back on the circle one, we would see some artifacts of how that fits, because you know, we see it looks more like a polygon that fits that. So so some activation functions are better than others for different things. And as always, with neural networks, as far as I know, anyway, as far as my experience has shown me, it's kind of more of an art than a science in optimizing neural networks. So there's all these hyperparameters in neural networks. You've got a number of hidden layers, you've got nodes in the different hidden layers, you've got learning rate, you've got, you know, are you going to use regularization? What firing functions are you going to, activation functions are you going to use? All these things. And you know, I think in the near future, we'll actually be more and more applying machine learning techniques to tuning the learning process, which should work out pretty well. But until then, and just experimenting around with this stuff, it's still a lot of art instead of science when we're tweaking these different parameters, these hyperparameters. Okay, so that's fully connected networks, and we're going to still in the vein of supervised learning, we're going to talk about some other network configurations after I take this question from my colleague.
So I think what you're mentioning where the tuning is more of an art, and early on you've shown this visualization of how the inner workings are, you know, of a particular network. I guess is that part of a challenge? Like what I've heard a number of times in the financial services industry is, you know, for anything that I need to do that's regulatory.
Anything, if there's anything I need to do that's what?
That's like some report that I need to submit to a regulator.
Regulatory. Okay.
What is the, like the fact that machine learning tuning is a dark art, and the inner workings are so complex, how do I prove the level of accuracy?
Okay.
That kind of-
Given that tuning a neural network is a dark art, let's start there. So it is an art, but you can quantify how well you've tuned it, right? So I wonder if I've got a resource for that. There are different scores that are applied that you can use to where you take your test data and you can you can test the accuracy. You know, there's like an F4 score and some other scores that have to do with false positives, false negatives, and those kinds of things, where you can quantify it pretty well, how accurately your network is predicting, right? So not only what the error is, but also you can test that with test data and kind of verify accuracy in different ways. So that's a different problem than being an art to train, because so it's an art, but you can train it to the point where you can exercise that art, right, to the point where you can verifiably prove that it's doing things accurately. However, if you have this new thing that you've never seen before, or you can people have hacked into neural networks, right, and tried to, and maybe given it some bad data and caused it to make bad predictions. And so there are going to be some disciplines that we need to do, similar to unit tests, right, or other tests where we continually monitor and make sure that the integrity of the prediction of the neural network is good. Yes.
No, I do agree with you when you said that it's some sort of an art, but I think the more you get to understand how these different functions work, the more you understand the heuristics behind tuning the hyperparameters in order to make your network behave in a certain way, or your model behave in a certain way. And also to what he was saying, like financial industries are becoming extremely, I have a word here, I was going to say, like, they are becoming more like strict in terms of how explainable some of these models are. So you're not going to see a big acceptance of using all these different type of techniques until there is good explainability behind the models.
Okay, so I want to repeat what you just said so everybody heard. So two things. One is, although the neural network training is an art, it's one that through training and experience can be exercised well. And the more training and experience you have, the better you're going to be able to do that, and the more scientific it becomes, right? But also, okay. And then the other thing is financial. Just the note that they are very strict in making sure that that it's verifiable that the results are accurate. So, okay, thank you.
Excuse me.
Yes.
Is there at the beginning you mentioned supervised learning, unsupervised, and reinforcement?
Yes.
Is this an additional method of analyzing data?
Okay, so is what an additional method of analyzing?
Neural networks.
Neural networks. Neural networks are typically used in supervised learning because the input are the features coming in, and the right answers are what you're expecting at the output. And so neural networks are typically used in supervised learning. Yeah, we're still talking about supervised learning.
Okay.
And but you can use neural networks in conjunction with the other two types of learning. So, yeah, thanks. Good question. Okay. Yes.
Could you
are you going to cover something reward-based learning?
Yes.
You did mention.
I'm going to cover reinforcement learning. Yes. Okay, so another type of neural network that's used in conjunction with fully connected networks is called convolutional neural networks. And it's typically used for images. So this page, if you click on this link, it comes up with an interesting, it comes up with the home page of a Stanford course on convolutional neural networks. And it's actually a functioning convolutional neural network which takes images and then makes predictions, sometimes incorrectly. I still have a number. Okay, so there's a horse, yeah, it's a horse, etc. So now, what does a convolutional neural network look like as far as architecture? So let's say that we're using it with an image. Let's say the image is 200 by 200 pixels. Well, we have 40,000 features. Well, actually, we have 120,000 features because of RGB. So 120,000 features of 0 to 255 each. And then we take them through one or more layers of convolutional and pooling. So convolutional, you can think of that as Photoshop filters, where it convolves the input, and maybe it's looking for edges, or it's doing some blurring or whatever. And then pooling is typically something like pixel averaging, where you may take 4 pixels and you average it into 1. And then you might have multiple layers of that, and then you would end up typically at a fully connected network like we've been talking about, and then some type of prediction, typically classification. Is the bird, is it a sunset? So there's this really nice visualization that a person by the name of Adam Harley created that I'd like to show you. Oh, I keep standing by that microphone. So here it is. And so this visualizes a convolutional neural network in the context of what's called the MNIST dataset. MNIST dataset is another very well-known dataset that was created, I think, in the 90s for being able to train handwriting recognition for zip codes. So machines could look at the mail and find out what zip code it needs to go to. So it was trained with thousands of handwritten digits from 0 to 9, and so this neural network has been this convolutional neural network has been trained with that. So we'll give it a number here. We'll just we'll do a 7. Maybe put a cross in it here for the fun of it, and we'll see that the prediction then is actually the highest probability is that it's a 9. I tried to fool it a little too much. I tried to mess with it. So maybe I'll try to make it more like a 7. Little bitty thing there. And so the prediction is that it's a 7 with a little bit of a probability that it might be a 6 or a 4 or a 3. And so internally then, here we have the input, and then we have a convolutional layer which contains several of these panels that then have convolutions here. And you can notice the lines between the input and each of these panels. And then here we've got pooling layers, which is just doing the probably 4 to 1 pixel averaging. And here's another convolution layer, working on that one. And then here's another pooling layer. And then here's the first fully connected layer, fully connected with all of the pixels, the numbers, and the neurons, whatever, in the last pooling layer. And then here we've got another fully connected layer. And this has 100 neurons in it. And then we finally have the prediction. Okay? So what's interesting about this last layer, in addition to being part the neural network that gets you from the input to the output, it's also a code for this, for the input. So through these convolutions and pooling and training, neural network training, we have this in Java speak, we would think of this as a one-dimensional array of 100 elements in it. In mathematics speak, we would say it's a 100-dimensional vector. But in any case, we have these 100 real numbers that represent this image through a process that ends up being called autoencoding. So we've reduced this down, this image down, and we've kind of encoded it into this 100-dimensional vector. And so we're going to use that later when we get into unsupervised learning. But I just wanted to make a note of that. Yes?
So as far as I understand it, and so this started as a model of the brain, human brain. In the human brain, there are also many layers. And the layers are specialized. So one layer recognizes edges and another recognizes shapes and that sort of thing. Do we think at all in terms of these layers that way, or are they just, hey, let's have two layers that are fully connected, they're indistinguishable, they just happen to work?
Okay, so to repeat the question, in the human brain we have layers, right? And some of them are specialized. And they've done experiments, as you probably know. I've got a gnat up here that's bothering me, so I don't have a tick or anything. Not that there would be anything wrong with that, but I'm just trying to shoo this gnat away. So they've done experiments with the human brain where they've had not experiments like inflicted damage on the human brain, but they've noticed that when there's been damage in the human brain, that other parts of the brain, maybe that are responsible for oral sound, maybe that's damaged, but maybe other parts of the brain have picked up on that. Right? So what we think of as being specialized is actually can be adapted to be more general or specialized for something else. Right? And so with artificial neural networks, that same principle is in play, where you have these very, especially with the pure, fully connected networks, you have this very generalized thing that can then learn very specialized things. And so the way it does that then, in those different layers, it tends to, I just swallowed that now.
Do you have a learning algorithm for that?
Wow, okay, anyway, I got rid of that. So what you end up with from the input all the way to the output, you have these high-level features here, right? And as you see them from the input to the output, kind of like this picture that I showed you just a second ago, where you see these high-level features that look pretty much like the input. And then notice that they look less and less like the input, and they start to generalize and even pick out common features of the input. And so that's kind of, as you progress through a neural network, whether it's convolutional or whether it's fully connected, you see that same kind of thing where in different layers, as you progress, the things that it's pulling out that it thinks are important because it's had to train it to be important, to get that error rate down, then it starts to decompose those things. So I'm going to now show you the one more point on this convolutional neural network that I wanted to make sure I gave you. Notice that here we have, and you reminded me of this to say this, by the way. Notice here that in this convolutional layer, it seems to be looking for different things, right? Maybe one place it's blurring a little bit, one place it's looking for edges, and here it's kind of changed, like these edges, it's got white there, but then it's making these black. And for some reason, it's doing different things. Well, those things aren't things that were pre-programmed, like you would say, I want this Photoshop filter that does this thing. What this is the result of is of the training that it did when it was trying to get the error out of the network. It learned that it needs to do this kind of convolution and this kind and this kind and this kind in order to get that error down. And so in that sense, we see, just like you said, we see these high-level features coming in, kind of being decomposed. And so that's kind of some intuition. Yes?
What is like for each layer becomes more and more convoluted, less like the original image? Like how does the training differ per layer in order to make that happen? Yes. So why is the first layer only slightly convoluted, and why did the further on layers become more convoluted? Like that's what they saw as like more important to be able to distinguish what that number is.
Okay, so there's two factors in there that I know of anyway. One, as far as like why do the layers look so different from each other? And so one reason is, like you said, is picking up things that are important to it, to being able to recognize that as a 4. Another reason is the dimensionality is being reduced here from, that's 20 by 20, from 40,000 pixels or whatever down to 7 outputs through here, which is 100 neurons. So that's part of the reason. Okay, so I'm going to go ahead and move on now to another type of neural network, or one that's used in conjunction with fully connected neural networks as well, and that's called recurrent neural networks. So to demonstrate that, I'd like to just talk about this idea of time series data versus one-time data. So everything we've talked about so far has been one time. Iris data flower, at a moment in time. A picture at a moment in time. What is this picture? But if you have a video or a GIF, then that's a different thing because that's time series data. So in this picture, if you showed this to a neural network and said, make a prediction what's going to happen next, it wouldn't have a clue because it's just a moment in time and it's only been, it might say, okay, there's 2 cats in a box, right? But if we had a GIF, we could see that, well, the next thing that's going to happen is that the cat on the top is going to close the box and the cat on the bottom. And so yeah, that was, I had to pick out just the right GIF for you all. So it took me about an afternoon. That's usually what I do in the afternoon. I was looking at GIF pictures. But yeah, so anyway, that time series data is a job for recurrent neural networks. And because it needs to be trained not only to recognize, like, instead of being recognized static images or things, it's got to be able to recognize sequences and predict then what is going to happen next in the sequence. For example, if you had a phone, everybody's got a mobile phone, you type a text, you type a word, and then it's suggesting the next word based upon the word you type. Or maybe it suggests a third word based upon the first 2 words. So it's very likely that was, what's behind that is a recurrent neural network that is taking your input and then consulting a recurrent neural network that's been trained on a lot of times it's your own history of making texts, but also of everybody else making texts. So the very simplified architecture for a recurrent neural network is over on the left. So over on the right is just one layer of a fully connected network. Over on the left, you notice the additions of the arrows that point back to itself. So in a recurrent neural network, nodes in a recurrent layer then point back to itself and in time steps, so iteratively. So as it's being trained with time step data, it kind of goes back into itself and then can learn sequences of data. And there are all sorts of different techniques like long-term short-term memory. Thank you. Wow. I have short-term memory. Long short-term memory, where you can have older memories fade, right? Because maybe they aren't as important if they're older, that kind of thing. So that's the overall architecture. So one interesting application that you can demo that with is Project Magenta from Google, Deep Brain or something like that, and where you can compose music. So the idea is they trained a recurrent neural network with songs, a body of work from Bach to Muse to wherever, and extracted the melodies as well as the rhythms. They trained a neural network. This is supposed to represent a recurrent neural network and the time steps in it. But let's say that you were going to compose a song, and so you start out with a blank sheet. And so it might say, on the melody side here, it might say, probability is that you ought to start with C. Then if I have a C, then I feed that back in, and then maybe it says probability based upon the way I've been trying, maybe the next note should be a C. And then if I have two C's, maybe the next one's a G, etc. Very oversimplifying that, but that's the idea. So then there's this really nice application that you can invoke just by clicking this link. And it's called AI Duet. And you can hit play here. And you can play it on, by clicking the mouse. You could have a MIDI keyboard connected, or you could just use your own keyboard. And so one of the first ones I wanted to play, just because it seems so much like Close Encounters of the Third Kind, they try to use that melody to talk to the alien spacecraft, only we're talking to an artificial neural network. I thought I'd play that melody. So it's a 5-note melody that goes like... So what it's trying to do then is it's trying to answer me back, feeding in what I fed, what I gave it, into that recurrent neural network, and then produce, the next few notes, kind of improvising with me, right? And so I could do maybe a standard, 3-chord progression here, and have it kind of answer me back in kind. So it tries to kind of answer me back based upon its training. And so I thought, well, maybe I could play the style of music that's called a round, which is like, row, row, row your boat, or Frere Jacques. And so I thought I'd experiment with that. Maybe it could play while I'm playing. So. It's a good way to fill an afternoon. So now we're ready for unsupervised learning. And if I had better supervision, I would have left more than 17 minutes. You didn't do a very good job supervising. So unsupervised learning is, remember, is this idea of training a model with unlabeled data and having it make sense of it. So I'd like to show you a demo then of another Google Arts. It's a Google Arts and Culture project where they took the artworks from hundreds of art galleries, and it's like thousands of artworks. And they wanted to be able to show a map of those artworks, a 3D map, but they wanted to show the artworks that were similar to each other in the same areas, right? So I'm honored to have a library scientist in the front row here. His name is Jeff, and we were kind of talking about you know, some Library of Congress things and metadata and that type of thing. And so in this context, you know, the typical way you would classify artworks is you would maybe take the artist or the artistic style, impressionist or whatever, and you would tend to tag or put metadata with these artworks. But that's not what they did, this Google Arts and Culture did. What they did was they auto-encoded, remember auto-encoding from the convolutional network? They auto-encoded these thousands of artworks into those, you know, 100-dimensional vectors. So it's these 100-dimensional vectors that we saw. As a matter of fact, I think in the Google Arts and Culture project, they went with something like 300-dimensional vectors, you know, because they wanted to have some good resolution in the encoding. So anyway, they took all of those, they made a 300-dimensional vector code out of each one of those. And so I'll show you the result, and then I'll talk about more about the approach. So if you go to that site, you can say begin guided tour, and here's the map over on the right. And then some human looked through these and said, you know something, I think that these artworks over here, those look a lot like ballet dancers. And so they made note of that area, and they put a little hyperlink here that would take you to that area, kind of like you would on a map. And so we'll zoom into that. There's all these thousands of artworks. And here's a region where clustered together are these ballet dancers. Again, no metadata, no tagging. It's all a result of auto-encoding all of these artworks into these representing them as each individually as a 300-dimensional vector. Again, an array of 300 real numbers. So how did they do that? Well, the auto-encoding we've kind of gone through. You know, it's convolution and training. But how do they then get those artworks to appear close to each other in this map? So part of that process is that they took these 300-dimensional vectors and they hung them into 300-dimensional vector space. That's a lot of dimensions. So let's talk about it in 2 dimensions. Let's say that each of those artworks consisted of only two dimensions, right? 2-dimensional vectors. So we could hang them into vector space. We could hang that into a vector space by hanging it here on the x and here on the y, and then we could compute its distance from the origin by using the Pythagorean theorem. So Pythagorean theorem, the square root of the sum of the squares, right? That's the distance between here and there. So let's say that I had 3 dimensions. So each of those artworks were encoded in 3 dimensional vectors. A vector with 3 dimensions, 3 numbers. So then I could represent that in 3D here by this point. So we have an x, a y, and a z. How do I calculate the difference, or the distance in vector space from that point to the origin? Well, I use the Euclidean distance. So the square root of the sum of the squares. So it's the same formula. And then what if I have 300-dimensional vector space? Because I'm hanging 300-dimensional vectors. Well, it's the square root of the sum of the squares of all the numbers in those 300 dimensions. So it's a straightforward formula. So I've got all these artworks, all these vectors hung in vector space. So if I can calculate the distance between an artwork in vector space and the origin, I can also calculate the distance between an artwork and another artwork. It's the same formula. It's Euclidean distance. So that's part of the thing. So now I've calculated the Euclidean distance between all of them. So then the other part of that is using this algorithm called T-SNE, which you can read about. There's links to it in here, but that's an algorithm for dimensionality reduction. In this case, reducing from 300 dimensions to a three-dimensional view. And so that's the result then, is this 3D map that we see. And so we could look at other things like, for example, armor. Somebody noticed that there were things that looked like armor in here. So then we can zoom into that map and yeah, so there's some armors. And again, it's all based upon visual similarity and hanging the auto-encoded 300-dimensional vectors into vector space. Questions? Pretty cool, actually. Yes, library scientist guy.
Well, I noticed in the ballet pictures there was like some G.I. Joes. Do these networks ever, are they capable of explaining themselves? Like, and it might answer some of the questions I heard earlier. It's like, well, why did you do that? You know, like, why did you put them with the others? And I think the answer is no, they can't explain themselves, but like when you ask a student, if you give them a problem and you say, how did you get to that answer? It could explain, the person could explain, this is how I got from A to Z. But are these networks capable of explaining why G.I. Joe ended up amongst the ballerinas?
Okay, so first of all, so the question is, the statement was, there's somebody that looks like G.I. Joe in these ballet dancers. I haven't seen that before, so I'm going to go look for that, just out of curiosity. Where's G.I. Joe?
He was like in the lower left. Yeah, just keep pulling.
The bottom. Is that guy?
No, back up. Keep back. Zoom out a little more.
Zoom out.
There he is. He's having a
there
cup
he
of
is.
coffee or something.
Wow.
Is it like an army of ballet dancers?
Go to the left.
There's one more, yeah.
Oh, yeah. Yeah, down in the auto encoding, there must have been some kind of visual similarity. That's a very interesting observation. Okay, so, and then your question then was, well, why did it do that? You know, and is it even tractable, right? And so it's really funny. I went to in Barcelona. I went to this NIPS conference. It's all about machine learning and neurons and things. And so some of the researchers, Jan LeCun, like who's the chief AI officer at Facebook, and others. It's funny, they're like Jan LeCun pioneered the convolutional neural network, and to hear people like him say, this is what these neural networks are coming up with, but we have no idea why. It's kind of like, okay, because when you have so many layers and so many numbers, and you can only speculate sometimes as to why it came up with that result. The important thing is that it got from the input to the output correctly. But yeah, so I need to leave it there because I want to get to machine learning. Reinforcement learning. I did want to say quickly, because I've got some colleagues back in this area that are doing these two handsome gentlemen back there right behind the camera are in a business that has to do with semantics, right? Translation, so there are a lot of words and stuff. And so one of the techniques you can use in natural language processing, and it's a pretty nice success story in unsupervised learning. It's called word-to-vec. And the idea there is that you comb through a body of work, like the works of Shakespeare or whatever, and then one technique is you take every 5 words as a bunch, and then you calculate the probability that the middle word is going to accompany the words, the 4 words on the outside of it. That's part of one of the ways that you can do this. And so then you just comb through the whole body of work. What you can end up with then is these n-dimensional vectors that represent a word, just like the artworks, only with words. And so you can then kind of play with those words. So if you hang those in vector space, you can see then the relationships between them, the semantic relationships, usually then mirror the relationship in vector space. Gender relationships here, plural relationships here. And if they're in vector space, because you can do addition and things on vectors, then like you can calculate distances and things like that. And so we can do things like king, the vector for king minus the vector for man plus the vector for woman. And then you end up with something that's very close to where the vector for queen lives. Okay, so that's one thing you can do. And so now I'd like to get into reinforcement learning. And so as a Java developer, there's a really great library for reinforcement learning called Burlap, and it's available at that address. And one of the very common reinforcement learning problems for experimenting anyway is grid world. And so you can think of this as a mouse, and this is a cheese. And so the mouse is going to try to get to the cheese, and and it has to navigate through these slits here. And so the actual rules for this particular grid world that I've created is that the agent, that's the mouse, can move left, right, up, or down. It gets a reward of 0 for each move. I could arbitrarily, I could say, well, I want a -1 reward or whatever, but I'm just going to not give it any reward for a move, but it's going to get a reward of 5 for reaching this terminal state. Agent can't move into a wall, and it can't move off the grid. And importantly, the agent does not have a map of the grid. It doesn't even know anything about grid world. The only thing that it knows about is it knows about states, like what state it's in. The state in the grid world is the row and column that it's in. And then it knows about rewards, if it received a reward. In our grid world example, it only gets one at the end when it gets to the terminal state. And then the agent, based upon the state that it's in and any reward that it got, then takes an action and tells the environment. And then the environment calculates the new state. It says, okay, agent, you are now, you were in 0, 0, you wanted to go up, and now you're in row 1, 0, row 1, column 0, and you got 0 reward. So the agent then takes that information, so then it's this iterative thing called SARS, SAR. It's just state, action, response, reward, and then state, new state. Okay. So then this application, Burlap, has an example in it that I modified, and it's in my GitHub repository you can get at. But the basic example is here, and so I'd like to run that for you. Burlap examples, and I'm going to run it here, and then I'm going to show you actually the console first. So the console output shows the episodes. An episode is when an agent gets from the starting point to get to the terminal state and get that reward. So in the first episode, it took 253 actions. And then, 935, and here over 1,000. So it's pretty much wandering around blindly. But then after a few episodes here, let's say maybe 32 episodes, it's getting it down to a pretty manageable number, and then after a while, pretty much consistently getting it down to in the 20s. So it seems to have learned pretty well how to navigate grid world. And so I'd like to show you then those episodes, the results of those episodes. So here's a visualization of grid world. remember this took lots of moves, and I'd like to just kind of show you the moves that it's taking. So first it tried to go south, which is illegal, and then it just kind of wanders around aimlessly. It's never had a reward, so it's just completely random. And I'll spare you some more randomness, and maybe we'll go here. And it's still completely random, right? It's right there next to it. Just maddeningly, finally, it gets the reward. But it's completely random. It doesn't know anything about the reward until it's gotten it there. And now, once it's gotten it, it can start to record, to make a note. Hey, I got a reward when I was in this state and took this action, right? And so then it can make a note of that, so then for future reference, to begin to learn how to get to that reward. And so maybe later, in episode, I'll just go to some random episode over here that looks shorter. Yeah, go to this one. So here we see probably some still messing around that lower left-hand quadrant. Doesn't have much of a clue, but once it gets kind of near, once it got around here, it kind of knew exactly what to do. So that should give you some insight on the reinforcement learning algorithm in that as it's getting the reward, and then as it gets to some place where it noted that it got a reward, through more and more episodes, the knowledge that it's gathering of how it got a reward and what value it places on being in a state and taking a certain action begins to radiate out. And so we see then this map that it's come up with by this time, to where it's, so these blue areas are the ones where it's experienced more. And so you see this knowledge kind of radiating out, and then you see these policies start to emerge. And these policies are the arrows saying that, if I'm here, my policy is going to be to take a right because, and I value being in this state and taking that action at 5 points, or doing the same thing here. And so that's that, and I'm at 8:31, so I hope I'm sorry, what?
Couple minutes.
Oh, I can have 2 more minutes? Okay. I can have 2 minutes?
Quick question.
Question?
In these 3 methodologies, we give some finite scope, right, to train the data or anything. Recently, we heard a news that Facebook created some neural network and it got out of control. What mistakes could lead for a neural network to get out of control?
Yeah, that's a good question to him, though. I don't know. No, I was kidding. Well, first of all, I heard that was an urban legend. The Facebook, there wasn't really this language that emerged that they talk to each other or something. So I don't know whether that's true. Do you know that it's true?
Yeah, there are some
true.
results that in the deep learning process, when we train a machine, we get some results. It resulted that it never listened to the instructor anymore, and it acted weirdly, and it's not even under control, and they completely shut down the whole process.
Okay, so that gets to the whole machine uprising. Is AI going to cause machines to uprise So Andrew, I'll end by quoting Andrew again. He tweeted when Elon Musk was all the sky is falling and all this, and AI is going to kill us all. Andrew Ng tweeted, worrying about AI taking over the world is a little bit like worrying about overpopulation on Mars. It could happen maybe someday, but we've got a lot of work to do between now and then. So I'm going to end on that. I thank you for your attention. And
thank you, Jim.